Hello everyone, welcome back to TechCognite. My name is Amit Kumar Garg and today we are going to learn about Kafka replication and offset management in details with multiple live examples. Let us quickly walk through the agenda of today's session. So this complete course is divided into three parts. In part 1 we covered about Kafka introductions, basic commands and then producer and consumer application. In part 2 we covered about Kafka topic, partition and consumer groups in detail with various examples. In part 3 we are going to cover about Kafka replications, and in Kafka replication we are going to set up a 5 node Kafka cluster and try to understand how replication work, what is leader, what is follower and what is ISR. Then we are going to jump onto the offset management where we will see what is lag, what is uncommitted offset, and then there is a property to set up auto commit true and false. So we are going to look about that one. And then finally we are going to see some advanced configuration to make our application better and to achieve the higher throughput. So what is Kafka replication? Kafka replication is to store the multiple copies of your data onto multiple nodes. Means single partition will be stored on multiple nodes, and we need this to deal with some unavoidable situation like network failure, disk failure, machine maintenance, etc. Let us now try to understand the same functionality through an example. So we have an application, we have a 2 node Kafka cluster, and we have one order topic with replication factor of 1, partition 1, means that there will be only single copy of this data will be stored, and in this example it is stored on node 0. Our application is connected to this Kafka cluster to serve their functionalities. So at this point everything is working fine, but at one day what happened that this node 0 goes down due to any of the reason, maybe the disk failure or the network failure. So at this time our application is not able to serve the functionality which depends on to the order topic, because the topic itself is not available, and that is because the node 0 has been gone down. Now to deal with the same issue, we save the multiple copies of our data. So assume that we have the same application, we have the same Kafka cluster, but this time this order topic is created with replication factor of 2, means that there will be 2 copy of data will be stored on 2 different nodes. So our application is connected with the Kafka cluster, and at some time, let's assume that node 0 goes down again, our application will not be impacted. It will still able to serve their customer because the same data is available with the node 1. And that is how we deal with the unavoidable situation in Kafka, and that is how we achieve the high throughput or high availability as well. Now Kafka replication is used to increase the fault tolerance as well, as we have seen in the previous example, and replication are set on per topic basis, and this is the best practice to set at least 2 to 3 replica for each topic. We may have the requirement to increase the number of replica, but minimum of 2 to 3 should be set for each topic. Now this is the command to create a tacognite topic with number of partition as 3 and number of replication factor as 3. That means for each partition there will be 3 copies of data will be stored on 3 different nodes. Now this is the describe command to see how many number of replicas are set for any existing topic. And during our demo we are going to see all this command running on a 5 node Kafka cluster. Now let us see what will happen if we will create a topic with number of partition as a 3 and number of replica as a 3. So if I will execute this command, it will create the 3 partition first of all. So tech0, tech1 and tech2 are 3 partitions for our tech topic. And then it will check the required number of replication. So here the required number of replications are 3. So it will create 2 more copies for each partitions to meet the requirement. Now there is a term called ISR, and ISR means that in sync replica, which tells us that how many nodes are containing the data for a particular partition. So as you can see in this case, 3 nodes are containing the data for this particular partition, hence the ISR is 3. When the ISR is equal to number of required replicas, means that cluster is in healthy state. But if ISR is less than the required number of replicas, means that cluster is unhealthy state and some manual intervention is needed. ISR can fall below due to network failure or due to any another reason when the broker is not available. When we create a topic with replication factor, Kafka first of all choose a leader. A leader can be any machine from the cluster. A leader is responsible to maintaining the desired number of replicas. To meet this requirement, Kafka chooses two of its peers as a followers. Once the leader and followers are established, a quorum is formed. Once quorum is formed, cluster is ready to take the load from producer and consumer. In Kafka, producer can send message to the leader node only. And that is because leader can take care of the topic requirements and meet the required number of replica for the topic. But at the same time, consumer can consume message from any of the node in the cluster. Either it is a leader node or a replica node. And that is to achieve the higher throughput. Let us see a quick demo. So for this demo, we are going to start five nodes Kafka cluster on our local machine. So as you can see, I am in config directory of Kafka server, and here we have created the 5 server.properties file. We just created the properties file using the existing one. We just copy that one and given some unique name 12345. And if I will open the server.property file, we just need to pass the unique value for three properties. One is the broker ID. So I have given the unique broker ID for all the properties file. Then the port. On the port, it is the 9092, and for the next, it is 9093, 9094, 9095, and 9096. And then the log directory. So here in the log directory, I have given the unique name. So if I will go on to the server 02.property file, you will find out that I have given the broker ID 2, listener port is 9093, and then the log directory is Kafka log. And in the similar way, I have created the 5 properties file. Now to run the 5 node Kafka cluster on a single machine, I will first start a zookeeper instance, and there will be only single instance of the zookeeper running. Then I will execute this command on 5 different command prompt, one for each server. So here you can see that I'm executing the Kafka server start command with the property 01, then 02, and the similar way I will execute this 5 times on 5 different server, 5 different command prompt, and that will start the 5 different Kafka server for us. I have started a 5 node Kafka cluster on my machine. Let us now create a topic. So here you can see I'm creating a test topic with replication factor of 5 and the partition count as a 3. So if I will hit enter, it will create a test topic for us. So topic has been created now. Now the topic has been created. Let us see the describe command. So here I am executing the describe command on test topics. So if I will hit enter, it will give us the detail of number of partition, number of replicas. So here you can see for this test topic, we have the partition count as a 3 and replication factor as a 5. And there are 3 partitions, partition 0, 1 and 2. For the partition 0, node 1 is a leader. For partition 1, node 2 is a leader, and for partition 2, node 3 is a leader. And for each partition there is 5 replicas are required, and replicas are on 1 2 3 4 5 nodes. Okay, and you will see that the in sync replica as well, which is called as a ISR, and ISR is also on the same machine 1 2 3 4 5. That means that the cluster in the healthy state, because the number of required replicas and number of ISR both are same. So the cluster is in the healthy state and everything is working fine in this case. As we can see, we have a leader on broker 1, broker 2 and broker 3. Let us quickly shut down one of the leader and see what will happen. So here I am on server 2, and if I will press the control C, it will shut down the server, and you can see the server has been shut down. Let us quickly do the describe command again and see what has happened behind the scene. So if I will do the describe command, you will see that the leader for the partition 1 has been changed. Previously the leader was a broker 2, but now the leader responsibility has been given to the broker 3. And here also you can see that the in sync replica has been fall below the required number of replicas. Previously it was on 1 2 3 4 5 machine, but now because we have shut down the broker 2, the in sync replica has been fall below. And this is the case when we will say the cluster is in unhealthy state and we need the manual intervention. And now if I will restart the same server, the cluster will come back and will join the cluster again. So here you can see that I'm starting the same cluster again, and if I will do the describe command again, you will see that the in sync replicas are again in sync. So here you can see that there is no change in the leader because there are no impact at the leader 3, so it is not going to be changed, but the ISR are again in the sync. So the cluster 5, so with the manual intervention we have started the cluster again, and you can see that the broker 2 has joined again, and the in sync replicas are again in as per the number of required replicas. So this again we can say that the cluster are back into the healthy state. So when we shut down the leader 2, what happened behind the scene is that Kafka come to know, okay, the leader which was on partition 1 has been shut down or not available. It will promote any of the replicas as a leader. So here the third node has been promoted as a leader because we know that the exact same copy is available onto the replica node 3 as well. And for the application there will be no impact because the consumers are still able to consume the messages from these replicas, and because the leader has been changed, the producer will able to produce the message using the broker number 3 now. Let us now see what is Kafka offset. So Kafka offset is a last read position by any consumer, and offset 0 means start of the messages. So here you can see we have a Tacognite topic. We have a producer application who is producing the messages to this topic, and it is continuously producing new messages as well. So if I will say offset 0, that means that I will receive this 0 messages, 0 message at first, and then the offset is going to be keep on incrementing by 1 2 3 4, and the poll function can return multiple messages at the same time. So let's assume that I have been received 3 messages in first call of poll function, then my offset will be 3. And if I will pass the hyphen hyphen from beginning, that also means that I am reading messages from offset 0. Kafka consumer itself keep track of consumer offset. Single consumer may have multiple offset, one for each partition. So if any topic has 5 partitions, Kafka consumer may have 5 different offset, one for each partition. Then we know that Kafka poll function can return multiple messages at once. Once the messages has been processed by the consumer, messages are committed and Kafka increment the committed offset. Committed offset are stored in a special topic created by Kafka. Name of this topic is underscore underscore consumer underscore offset. This consumer group command is used to get the number of total consumer in a group and on which topic they are reading from. What is their current offset, what is their current lag, what is their committed offset. All this information can get from this command. We are going to see the output of this consumer group command in a minute in our demo. Let us now understand some of the terminology of Kafka consumer offset. So here we have a topic named Tacognite with partition 0. Partition 0 contains some of the messages. Offset 0 means beginning of the messages. Current position means the number of messages which has been read by this Kafka consumer. Last committed offset means the number of messages which has been successfully processed by the Kafka consumer. Difference between last committed offset and current position means the uncommitted offset which is currently in progress or which is currently in processing. Then the producer application is still producing new messages. So the last message which has been produced by the producer application called log and offset, and the difference between the current position and log and offset means is the lag which is the number of messages which are yet to be processed by the consumer application. Let us now understand Kafka offset from an example. So I'm on in sixth example, com tacognite sixth, and here we have created a consumer application. We are passing a group ID as a demo. We have created a tacognite topic with partition count as a 2. So I'm listening on the same topic only, and here you can see that I'm consuming messages in a while loop, and I have put up a thread.sleep intentionally for 20 millisecond so that I can show you the lag information. So if I will do a run as Java application, it will start a consumer application. and it will be listening on to the Tacognite topic, and it has the group name as a demo. Right now we do not have any message, so that's why it is just waiting for the messages to come. And in the same manner we have created a producer application, and in the producer application also we have created a while loop, which is the infinite while loop. And here you can see that we have put up a thread dot sleep of 10 millisecond only, and consumer is consuming into the speed of 20 millisecond. So this is to generate some lag and show you the important information. So if I will do run as Java application, you will see that it will start putting up the messages and consumer will start consuming the messages. So let us quickly jump on to the command prompt, and if I will go here, you can see that we created the Tacognite topic previously with the partition 2. And if I will do the describe command on group demo, if I will hit enter, you will see that there are two rows are coming, one for each partition. So you can see that we have two row for Tacognite topic, and there is the current offset information and the log end information and the lag as well. So previously I created this demo group on test topic, so that information are also present here, but now we are listening on the Tacognite topic only. So you can see that the log end offset is the number of record which has been produced by the producer, and the lag is number of record is yet to be consumed by the consumer, and there is one consumer connected with this demo group. And if I will do again, you will see that the number is changing because the consumer and producer both are consuming their messages and producing their messages at their speed. So you can see that the current offset is 802, log end offset is 1850, and then the lag is there. So it will keep increasing because we have set up our application in this way that the producer will produce more messages than the consumer will consume. And you have the information of partition as well here, so we can see that how many messages are left to be read or consumed by consumer in case of partition 0 and partition 1. And if we will see that the lag is increasing, in that case we will have to start more consumers, or we may have to increase the processing speed as well. Next is how Kafka come to know which message or which offset need to be committed. For this, Kafka used two properties. First is enable.auto.commit, which tells Kafka who is going to commit the offset. Is Kafka need to handle, or consumer itself will call the commit function? Default value of this property is true, which means Kafka will have to call the commit function. The second property is auto.commit.interval. This is the time after which all read messages are going to committed by Kafka if auto.commit interval is set as true. For example, if we receive any message just now, Kafka will commit that message after 5 seconds, which is the default value of this property. We can change both the value in our application if we want to handle the commit logic ourselves. If auto commit is true, Kafka will commit the offset after the interval regardless that the consumer has processed that messages or not. Kafka may redeliver the messages if consumer failed to call the commit function. Assume that I just read the messages and my consumer application goes down. In that case, our consumer client will not get chance to call the commit function. So after rebalancing, the same messages will be delivered again by the Kafka to the new consumer. Always remember that if something is read does not mean that is committed as well. If auto commit is equal to false, then the commit function have to be called by consumer application manually. And if auto commit is true, the Kafka will going to be commit after the interval from the consumer application only. Consumer can set auto commit to false to manually manage the offset. In this case, consumer will have to call the commit function to enhance the offset. There are two methods to do this. One is the commit sync and second is the commit async. So first one is the commit sync method, and we call the commit sync method when we do not want to receive new messages until the current message has been committed successfully. So what we do, we receive some messages from the Kafka, we process them, and then finally we call the commit sync method. Okay, so commit sync is synchronous in nature. What that means that when we call the commit sync method, the application is going to wait for the response to receive from the server that the message has successfully processed or the commit message has successfully committed. Okay, in case of exception, so if we call the commit sync method and we receive one exception, in that case it will automatically retry. It will automatically retry to commit that messages, and it will retry until it has been succeed. Otherwise, it will not going to receive any new message. So there is a property retry.backoff.millisecond to reduce and increase the interval, because right now it is sending the event in every 100 milliseconds, so we can increase that interval and decrease that interval with this setting. Next is this feature is used to receive or to achieve the highest consistency, because if the message has not been committed, it is not going to pull the any new message. So that's why we are saying that in case of high consistency we use this function. With commit sync function we receive the highest consistency over the throughput. Next one is commit async, and as the name suggests, this is asynchronous in nature. What that means, so we receive some messages from the Kafka, we process them, and after that we call the commit async function. This commit async function will exit immediately or will give the response immediately and start pulling up the new messages. It will not wait for the actual response from the server whether the message has been processed successfully or not. In this case, we are not going to know when the commit is succeeded or not, and if there is an exception the Kafka is not going to retry. So what will happen, what we can do, we can set up a callback to understand whether the commit has been succeeded or not, and that callback is going to be called in both of the scenario, whether the commit has been failed or commit has been succeeded, and we can take our action based upon the response we received from the Kafka. And because this is asynchronous in nature, non-blocking in nature, we are going to get the higher throughput, because as and when we call the commit async function, it is going to return me immediately, and then we will start pulling up the new messages and start processing the new messages instead of waiting of the Kafka to get the response that whether the message has been successfully processed or commit has been successfully made or not. So here in the example, you can see that we can set the enable.auto.commit as a false, and then on the Kafka consumer, we can call commit async function. In the similar manner, we can call the commit sync function as well. Next is message retention. In Kafka, each message has some retention period, means messages are not going to deleted immediately even if the single consumer has read that message. Default retention period is of 7 days, and this period can be set per topic basis. This can be changed with the property hyphen hyphen config retention.millisecond while creating the topic. By default it will use the 7 days, and if you want to change it we can use hyphen hyphen config retention.millisecond and pass the millisecond desired for the particular topic. Then to deal with this low consumer, this retention period is very useful as the messages are stored for the longer duration, so low consumer can consume the message in their own pace and it does not miss any message for the slow consumer as well. In a high load system, sending each message to Kafka broker may impact to the system performance. In this case, we can use Kafka batch processing to achieve the high throughput. In case of batch processing, Kafka create multiple batch for each partition, and collection of all the batches are called the buffer. There are some property which are apply at single batch level and some property apply at buffer level. First property is batch.size. This tells Kafka to flush the batch if maximum number of configured bytes are reached, and this property is applied to per batch level. Next property is buffer.memory, maximum number of bytes that can contain all the buffer. If it reaches to the threshold, messages are going to push to the Kafka. Next is max.block.millisecond. This configuration is used only when buffer.memory is full. As all the buffer are already full and going for flush the message to the Kafka broker, this configuration block the send method to push any new message in this buffer for the particular time period. So linger.millisecond, this configuration is used if we received one record but batch.size and buffer.memory are not met. So in that case it will wait for the configured millisecond. If that has been reached, So it, without looking into the batch.size and buffer.memory, it will push that message to the Kafka broker. Next is message durability, means that when producer application is going to say that message has been successfully pushed or successfully received to the broker node. So for this one we have the property called ACKS, and this property can be set with the properties tag with the producer application. This property can have three values. One is 0, which means fire and forgot. And if we are sending the messages which are not very much important, we can set this value as a 0, which will give us the higher throughput. If we will set as a 1, that means the leader of the partition should acknowledge. And once the leader has been acknowledged, we will assume that the message has been pushed to the Kafka broker successfully. But we have one another property which is all, which means that all in sync replica should confirm that message has been received successfully, and in this case we will get the highest consistency but the lower level of throughput. Next configuration is retry. In case of error response from the broker, how many time we want to retry to push that message. There are two configuration for this one. First is retry, number of time we want to retry if fail. Second is retry dot backoff dot millisecond, how many millisecond my application will wait for the next retry. And we can set both of these properties or both of this configuration with the properties. Now there are some configuration for the consumer application. First configuration is fetch.min.byte. This configuration is used to set the minimum number of byte must be returned when the poll function is called. Next configuration is max.fetch.wait millisecond, and this configuration is used to set the total time duration our application will wait when broker do not have enough data. Next configuration is max.partition.fetch.size. This configuration is used to set the maximum number of bytes that will be fetched per partition basis. This setting is important when single consumer is consuming messages from multiple partition or multiple topics. Next is max.poll.record, and this is to set the maximum number of record allowed per poll cycle. In Kafka, each consumer application sends heartbeat to the consumer group coordinator. If consumer not sending the heartbeat, group coordinator will assume that the application is not alive or not in the healthy state and will start the consumer rebalancing. Heartbeat.interval.millisecond configuration set the interval time duration after which consumer should send the heartbeat call. Next is session.timeout. If heartbeat is not received from the consumer application, how many duration consumer group coordinator will wait to initiate the consumer rebalancing. With this, we come at the end of this session. Thank you very much for watching this video. If you have any question or doubt, you can ask in the comment section. I will try to reply as soon as possible. If you like the video, hit the like button and subscribe to this Techognite channel. Thanks again. See you in next video.